that the answer to the Big Bang riddle lies in the movements of these giant brains.
It's so simple. Here's a brain on which we live, and here's another brain floating in the higher dimension. There's absolutely nothing difficult about imagining that these collide with each other.
According to this idea, sometime before the Big Bang, two brains carrying parallel universes began drifting toward each other. Until
all of that energy has to go somewhere. Where does it go? It goes into the Big Bang. It creates the expansion that we see, and it heats up all the particles in the universe in this big fiery mass.
As if this weren't weird enough, the proponents of this idea make another radical claim. The Big Bang was not a special event. They say that parallel universes could have collided not just once in the past, but again and again. And that it will happen in the future. If this view is right, there's a brain out there right now headed on a collision course with our universe.
So another collision is coming, and there'll be another Big Bang, and this will just repeat itself for an indefinite period into the future.
It's an intriguing idea. Unfortunately, there are a few technical problems.
Well, that was a very ingenious scenario that arose naturally within string theory. However, the good old problems creep back in again.
The fact is, we don't really know what happens when two brains collide. You can wind up with the same situation we had with the Big Bang. The equations don't make sense.
They have to make a lot of assumptions in their models, and I don't think they've really solved the problem of the Big Bang in string theory.
If string theory is the one true theory of the universe, it will have to solve the riddle of the Big Bang. And there's a lot of hope that someday string theory will succeed. But for now, there's also a lot of uncertainty. As promising and exciting as the theory is, we don't entirely understand it.
It's as if we've stumbled in the dark into a house which we thought was a two-bedroom apartment, and now we're discovering is a 19-room mansion at least, and maybe it's got 1,000 rooms, and we're just beginning our journey.
So, how sure are we that the universe is the way that string theory describes it? Is the world really made up of strings and membranes, parallel universes, and extra dimensions? Is this all science or science fiction?
Well, the question we often ask ourselves as we work through our equations is this just fancy mathematics, or is it describing the real world?
These exercises in our imagination and mathematics are all, at the end of the day, subjected to a single question. Is it there in the laboratory? Can you find its evidence?
String theory and string theorists do have a real problem. How do you actually test string theory? If you can't test it in the way that we test normal theories, it's not science, it's philosophy. And that's a real problem.
Strings are thought to be so tiny, much smaller than an atom, that there's probably no way to see them directly.
But even if we never see strings, we may someday see their fingerprints. You see, if strings were around at the beginning of the universe, when things were really tiny, they would have left impressions or traces on their surroundings. And then, after the Big Bang, when everything expanded, those traces would have been stretched out, along with everything else. So, if that's true, we may someday see the telltale signs of strings somewhere in the stars.
But even here on Earth, there's a chance we can detect evidence of strings. This past year in Illinois serves as command central for a lot of this research. Well, actually, the real work happens underground, where the hunt is on for evidence supporting string theory, including extra dimensions.
Not too many years ago, people who talked about large extra dimensions would have been considered crackpots, to put it lightly.
But all that has changed thanks to string theory. This is Fermilab, and right now it's our best hope for proving that extra dimensions are real. Fermilab has a giant atom smasher. Here's how it works. Scientists zap hydrogen atoms with huge amounts of electricity. Later, they strip them of their electrons and send the protons zooming around a 4-mile circular tunnel beneath the prairie. Just as they're approaching the speed of light, they're steered into collisions with particles whizzing in the opposite direction. Most collisions are just glancing blows, but occasionally there's a direct hit. The result is a shower of unusual subatomic particles. The hope is that among these particles will be a tiny unit of gravity, the graviton. Gravitons, according to string theory, are closed loops, so they can float off into the extra dimensions. The grand prize would be a snapshot of a graviton at the moment of escape.
And then the graviton goes to the extra dimension, and then it shows in the detector by its absence. You see it by its absence.
Unfortunately, Fermilab hasn't yet seen the vanishing graviton. And the pressure is on, because another team is hot on the same trail. 4,000 miles away, on the border of France and Switzerland, a lab called CERN is constructing an enormous new atom smasher. When it's finished, it will be 7 times more powerful than Fermilab's.
There's a great sense of urgency that every minute has to count, but eventually CERN, our rival laboratory, will, frankly, blow us out of the water.
CERN will blow Fermilab out of the water not only in the search for extra dimensions, but other wild ideas.
At the top of the to-do list for both labs is the hunt for something called supersymmetry. That's a central prediction of string theory, and it says in a nutshell that for every subatomic particle we're familiar with, like electrons, photons, and gravitons, there should also be a much heavier partner called a sparticle, which so far no one has ever seen. Now, because string theory says sparticles should exist, finding them is a major priority.
So it's a big discovery to find supersymmetry. That's a humongous discovery, and I think it's a bigger discovery to find supersymmetry than to find life on Mars.
If we were to hear tomorrow that supersymmetry was discovered, there would be parties all over the planet.
The problem is, if they exist, the sparticles of supersymmetry are probably incredibly heavy. So heavy that they may not be detected with today's atom smashers.
The new facility at CERN will have the best chance once it's up and running in several years. But that won't stop the folks at Fermilab from trying to find them first.
The competition is friendly and fierce at the same time. We're competing like bad dogs, essentially. And it has always been like that, and it will always be like that.
We have to make sure that we don't make any mistakes, that we do absolutely the best we can do with these experiments, and take advantage of what is really one of the great golden opportunities for discovery.
If we do find sparticles, it won't prove string theory, but it will be really strong circumstantial evidence that we're on the right track. Over the next 10 to 20 years, the new generation of atom smashers is sure to uncover surprising truths about the nature of our universe. But will it be the universe predicted by string theory?